Welcome everybody to the experimental testing for aerospace structures course. Today we are going to have our laboratory activity number 3, and this laboratory activity is on the digital signal processing. I will share with you the text of this laboratory activity, and we are going to dig into the problems that are related to the aliasing, to the leakage, and to the estimating issues, estimating of the frequency response function or impulse response function, according to if you are talking about time or frequency domain. So in order to do that, I'm going to use Matlab. Matlab is a very useful tool to play with matrices, numbers, functions, plotting, and then it is a preferred tool here in this course because with a very few instructions you can do a lot from the digital signal processing point of view and also for other things. Now I'm going to show you my Matlab screen. I hope that all of you can see that. It is the typical Matlab screen that is divided into 4 sub-screens, 4 sub-windows. The upper left is the windows related to the data handling, okay, files, directories, and so on. On the bottom left, we are having the workspace window in which all the variables, all the arrays that we are going to use during our analysis are listed, and a very simple remark on the dimensions and type of those variables is reported. Then in the upper right window, we are the editor window in which we can edit our own M file. And then at the bottom right window, we are having our common window that is used to enter your instructions, enter your whatever command in the Matlab language. So the first problem that we are going to see together is the aliasing problem, and for that I wrote a Matlab script. These Matlab scripts are always referred to with an extension, file extension with the M, Matlab, okay? So as you can see, this Matlab script is called aliasing.m, and within inside this file, I have reported all the instructions or the commands that we are needing. Okay, so for this laboratory activity number 3, sorry, the first problem is related to the aliasing, and we are going to consider 3 sinusoidal signals having each a frequency of 20, 80, and 100 Hertz, 120 Hertz. Okay, and then we are going to sample this signal using a sampling frequency equal to 100 Hertz, and then going to record this, to observe this signal for a total time equal to 10 seconds. Okay, so I don't know if you are aware about all the Matlab instructions and the grammar within the Matlab code. Okay, but I'm going to detail you all these instructions. So the first instruction that is here, that you can see emphasized, is just a simple instruction that tells the Matlab clean, erase all your data that you have stored in your memory, all your windows, all your pictures, whatever. Okay, so just to start your program without having any other variable that could be a problem within your own Matlab code. Then I start defining your FS, that is your sampling frequency. In our case, we are having 100 hertz. We are not going to use any unit of measure at all because the Matlab is just receiving as input just numbers. It is up to you to introduce the numbers that are consistent with all the unit of measure that you are requiring. Okay, so I am introducing T, capital T, that is the total recorded time, 10 seconds. And then the first time variable that I'm going to define here is the time in which I have knowledge about my signal. So this small t here is a variable that goes from 0 up to the total overall time with an increment equal to the sampling time. That is just equal to 1 over the sampling frequency. In order to see that, I suggest you to go back, I think 1 week in time, in order to see what are the general relations between the sampling time, sampling frequency, observation times, and frequency resolution. Okay, so that you have all the things together in one shot, but we already dealt with that. And then because we need the dimension of this vector of time in which I know all the signal, I'm just introducing this number capital N that is referring to the number of sampling times that I have. Okay. Then, in order to introduce these three sinusoidal waves, I am define here three variables, P1, P2, and P3, that are the three frequencies that I'm going to use, 20, 80, and 120 Hertz. And therefore, here, I am just defining the first signal, that is a sinusoidal wave of frequency P1, that is 20 Hertz. The second signal, X2, is a sinusoidal wave, once again, with frequency equal to P2, that is 80 Hertz. Finally, X3, the third signal, sinusoidal wave with frequency equal to 120 Hertz. Okay. Please note, for those of you that are not familiar with the Matlab code, I'm always using the hyphen sign in order to not to have the replication on your common window of all the instructions that I'm going to give to Matlab. Okay. Then I'm going to move from the frequency domain to the from the time domain to the frequency domain. And in order to do that, I'm going to use what I have called the Fourier transform. Here, from the numerical point of view, we are using the discrete Fourier transform, DFT. Okay, and this is done using the fast Fourier transform FFT command within the Matlab code. And how I can do that? The capital X1 is equal to the FFT, that is the Fourier transform of your X1 signal. I'm going to do that for X1, for X2, and X3. Then I'm just introducing the vector of the frequencies, that is, as you know, the number of sampling times that are multiplied by the number of sampling points. Okay, and that is what we are going to have in order to have the vector of the frequencies. So from at this point, what we got is mainly three signals that are represented both in time and in the frequency domain. And then it is very nice to show what are these behaviors. Okay, so I'm going to create one figure, and I'm going to create three subplots, okay, within these figures. Okay. As a remark for you, the subplot command tells me that this figure is composed by three subplots as a row, one subplot as a column, and now I am plotting the first of them. And the command to have this plot is simply a y-axis, and then some properties. For example, could be blue is the color of this line. Okay, and so far what we got for all these three plots, x1, x2, x3, and then just to have that in different subplots, all these three signals are all reported. I made the same plot now in the frequency domain, okay? But now, of course, I have to plot the f, that is the frequency vector, or the vector of the frequency that I'm going to use, and I have just reported the amplitude, or the absolute value of the Fourier transform of my first time domain signal, x1, okay? And I have to divide that in order to normalize all of these quantities in order to have the right representation of the quantity of the signal in the frequency domain. I have also add a title plot here is some x label, y label, okay, as we did before, just to have a complete understanding of what we are having. Okay, I think that the commands here are quite easy to understand, nothing special. However, if you are in troubles in understanding this, you can always write on the command window help whatever name of your command, okay, within the Matlab functions, and then you will have in return a description on the usage of that command. Okay, so just in case you can have help online from the Matlab window. Now let's have it together. Let's run it. So the name of this M file is Aliasing. So let me recall it, Aliasing, and then let's go. Sorry, my computer is very, very, very slow, and so you have to wait for a while. So what we are going to have here is what we are just brought before. We have the first, second, and third signal, okay, in blue, in these three different colors, okay. And do you feel that there is something special in what we are seeing, what we are watching at in this signal? Do you have a comment that you want to share with all your colleagues? I put it here. What do you think about? Do you have a clue? Is that what you were expecting? Why?
C'è un problema di aliasing?
Yes, of course. There is an aliasing problem. Why? Now, if you, I'm leaving here the plot window, the figure window. So as you can see, I set my sampling frequency equal to 100 Hertz. If you remember, your aliasing problem, okay, is telling you that your sampling frequency should be higher than half of the max. It should be higher than twice the maximum frequency of interest. That is, by choosing a sampling frequency of 100 Hertz, your maximum frequency is equal to 100 divided by 2. That is 50 Hertz. Now, if you look to your sinusoidal waves, the frequencies are the first one 20, the second one 80, the third one 120. So because the maximum frequency is 50, only the first signal is good, is well represented, okay? Whereas the second and the third signal are not well represented at all. And moreover, there is also a, let me call that as a mirroring, or as we did during our classes, as we considered during our classes. And so the frequency of 80 Hertz is mirrored with respect to the frequency of the maximum frequency, that is 50 Hertz. So it is viewed in your analysis as a sinusoidal wave having the same frequency of 20 hertz. So the second signal is having the same frequency as the first one. But also the third signal, 120, is having the same frequency in this discrete world because it is mirrored twice, okay, with respect to the 50 hertz maximum frequency. And so all these three representations are looking the same, not just because they are having the same frequency, but because, as your colleague pointed out, there is an aliasing problem. Now, if you look to the second picture here, we are having the same view as before in time domain, but now in the frequency domain. First, remember, when we are taking the Fourier transform, we have to consider both the negative and the positive frequency. Remember, there is a symmetrical or antisymmetrical according to what kind of part in the frequency domain we are seeing, that is the imaginary or the real part, okay? Using Matlab, all this information is transformed into positive frequencies, okay? So all your frequency lines are reported in the positive frequency. The result is that only half of the frequency range that we are using is the good one. The other, the higher frequencies with respect to the maximum frequency, that is 50 hertz, is just a memory of the low frequency. So in these pictures, what we are seeing is just the whole two-side frequency domain representation, but actually only half of this frequency is good. That is from 0 to 50 hertz. The other contribution, the higher frequency contribution, is just a replication of what we already have in the lower frequency range, and it is a mirroring with respect to the maximum frequency, that is 60 hertz. So, having said that, and looking just to the first 50 hertz range, and what we are saying is that the first signal x1 is characterized by a very nice peak at 20 hertz, and that is what we got. Okay, so as you can see in the label, x1 is equal to the sine 2 pi 20 hertz times t. Okay, and that is the frequency domain representation. Just one spike, that is that we have just an amplitude, okay, of 0.5, that is half of the amplitude in the time domain as expected, okay, and is active at 20 hertz. If you now look at the second and the last plot, that is the one of the second and the one of the third signal, what you can see is that you are having just the same spike, the same frequency domain representation. And that is the frequency domain problem of the visualization of the aliasing problem, as we already pointed out. So there is a mirroring with respect to the center frequency, maximum frequency, sorry, that is the center here in this plot, 50 hertz. So we are seeing everything at 20 hertz. Okay, now let's move to the next step. Okay, the next step, what we are having is, let's see if we can have additional discussion on this aliasing. Let me introduce, for example, the downsampling. That is just, let's assume to consider only one after a given number samplings in your measuring, in your recorded data. Okay, so instead of considering all the time samples, I'm considering, for example, here every 2 or every 4, just to give you an idea. What does it mean that? It means that by doing that, we are resampling your time domain data, your recorded data. That, by the way, could be very useful if you have very, very, very long time sequences. Therefore, you need to reduce the number of data that you have to handle using your whatever numerical code. But doing that, you are entering once again the aliasing problem. Okay, because by doing this, by doing the resampling, then you are changing the sampling frequency, and therefore you will have the wrong identification of your time domain signal and the frequency domain. Let's evaluate that using this Matlab code. We are introducing the two sampling factors here, that is every 2 or every 4 sampling data, and therefore we are just rewriting your signals y1 and y2, that is every ds1 or ds2, that is sampling vector, and the corresponding time t1, t2 as the same. The corresponding sampling frequency that is different, very different, so we have to reduce one. So this is the corresponding new sampling point for the downsampling one, and the corresponding this one, and the corresponding new sampling frequency for the second downsampling factor. Okay, then let's see what happens in the time and the frequency domain. We have just to perform the discrete Fourier transform once again of the new time signal, sequence y1 and y2, and therefore let's plot the result. Let's see what happens by plotting these new results. Okay, and therefore press enter here. Here we go. We got two features once again. So here we have the first one that is in the time domain. We have the original blue line, that is your original sinusoidal wave that has been sampled using a 100 Hz sampling frequency. The others are circle, are the one that are using the new sampling time, that is every 2 sampling, so the downsampling number 2, and the downsampling number 4, so 25 Hz. Circles and crosses. As you can see, you have just a limited view of your time domain signal. But the most important thing to me is that what is the one that you can have when looking at the frequency domain picture here. And as you can see, you have a completely wrong result if you consider the new sampling time. So if you are having the first, if you consider the first line in which the bandwidth is 0.50 Hz, you have a very good synthesis, good identification of your original signal that I remember you is having a frequency equal to 20 Hz. Okay, if you reduce the sampling time, therefore you have also an additional frequency that is always 20, and 30. That's because the new sampling time is having the maximum frequency equal to 25, so there is a mirroring of 30. And when you are referring to the second downsampling, the maximum frequency is half of the 50 Hz, so 12.5 Hz. And therefore we have a completely wrong identification of your time domain signal, because as you can see, there is a frequency identification of 5 Hz. That is not the one that is good, because the original sign is vibrating at the 20 Hz, not 5. Okay. Good. Now, the third case that we are considering is the same approach as before, that is a reduction of your number of data, because maybe there are a lot. Instead of using a decimation technique that is using a certain number of data with respect to the initial one, we are doing that by introducing also a different low-pass filter. That is a new aliasing filter that is taking into account the new sampling frequency. And that is done simply by the Matlab command resample. This resample is the decimation technique. You are telling the Matlab that the new data, y1, for example, here, okay, is the old one, that is x, but with the new sampling frequency, that is the FS1, that is the one that is being obtained using the previous decimation technique, okay? And we start with the FS, that is the original sampling frequency. By doing that, the Matlab function result is already is introducing by itself the low pass filter that takes into account this change of sample frequency, and that is very useful. Okay, now we apply this idea of the decimation technique that has been done by Matlab using the resample mat and file. Okay, function by introducing two frequency, one at 5 and the other one at 30 Hz, so that we are now dealing with a signal that is the previous one having the 20 Hz plus these two additional frequencies. So we have what we call a color uh, signal in time domain because it is having more than one frequency. Then we made the same approach as before. We made the Fusilier score of the original signal and then the one with the sampling. Okay. Let's see what happens. Here we are having the result. As you can see, the resample function is taking into account to the new frequency, to the new sample frequency. So, for example, look at the first line. We are having the first plot in the frequency domain, in which we are having our sinusoidal wave characterized by the fifth frequency, the first frequency at 5 Hz, then 20, and then 30. Because the sampling frequency was 100 Hz, we are okay up to 50 Hz. So all of these three frequencies are good for us. The second line, the center one, because we are having, remember, a downsampling of 1 or 2, that is that our sampling frequency from 100 is shift to is lower to 50, and therefore the maximum frequency would be 25. And as you can see, the decimation technique, the resample, is currently taking into account the only two frequencies that are in the frequency range Z025. Okay, so we clearly understand, we clearly see the frequency at 5 Hz and 20 Hz. Of course, we are not having any good information for frequency higher than 25 Hz, although there is the mirroring of 20 Hz with respect to 25 that is acting at 30 Hz, but that is a wrong identification because remember, this center plot is good up to the maximum frequency that is 25. The lower one, once again, we are having the decimation techniques that the decimation that is lowering to a factor of 4 your data, that is your maximum frequency is 25 divided by 2, that is 12.5 Hz, and therefore just only the Hz, 5 Hz frequency is the good one. We can't have any other information with respect to the true signal properties because of the sampling frequency. But what we got in that frequency range is the good one. There are no aliasing, there are no mirroring that could be leading us in a wrong identification. Okay, so that is very interesting from the aliasing point of view. You will have in the course website the laboratory activity number as free text that is changing a little bit these numbers, and therefore you are kindly requested to write your report in which you write your discussion on this new data and therefore on this new result that you will go into. Leakage now. Let's see what happens with the leakage. So let me show you the Matlab file. Okay, once again we start with a boot command that is clear everything. We are now introducing an amplitude and frequency of 1 Hz, for example. The corresponding period is 1 over the frequency, so it is 1 for this case. And we are using a sampling rate, okay, that is 10 times the period. therefore, we are introducing two times T1 and T2 that are the truncated data. Okay, the first one is over 1 period, the second one is 5 periods. Okay, then we build the time domain vectors, and then we made the Fourier transform, and then we plot the result. Okay, so now we are plotting the result both in time and in frequency domain. That is referring to a signal with a given amplitude that is sampled for a finite number of periods. Let's see what happens. Okay. Here we go. So the solid line, blue or red, is the original signal having 1 hertz this time that is sampled, that is recorded for the whole time period 1 or 5 times the period. Okay, and then the dashed lines are the replication of that. Okay, as you can see, this is the connecting point because of the plotting issues, of course. But as you can see, when you let's say see this picture from the Fourier transform point of view, there is no discontinuity when you are periodizing your signal. Okay, when you are performing the Fourier transform. Okay, so your sinusoidal waves are still there. There are no discontinuities at all. And indeed, when you look at the frequency domain representation, okay, when using 10 or 50 times or 50 samples, what you got is your perfect identification both in the amplitude and in the frequency of the properties of your signal. Okay, of course there are differences between the lower and the upper plots because the number of samples are different, but the frequency identification, the property identification, the frequency domain is practically perfect. So we are very happy. Now, let's see if we are not using an observation time that is equal to a finite number of periods. Okay, so for example, let me consider that we are using a recording that is equal to 1.5 or 3.5 periods. Okay, what happens to our analysis is giving us the same information. Moreover, here I'm using what is called the zero-padded technique. Yeah? That is a typical technique that is used to fictitiously increase the resolution of your frequency domain analysis just by adding a proper number of zeros to your signal. As it were a longer signal than the recorded one, and because we are adding more numbers that are all zero. They are not contributing at all to the system information. They are not giving to the signal any additional information because they are just zeros. But what we are doing is just we fictitiously increase the resolution because we are increasing the number of sampling points of recorded data. Okay. Now let's see what happens. Here we go. Now, what happens here is that because we are observing the same sinusoidal wave, but with a longer and not final period of observation time, is 1.5 or 3.5, from the eyes of the Fourier transform subroutine, here we got a very nice discontinuity, as you can see. Indeed, the solid lines are not connected to the dashed line. That's because the observation time is not equal to a multiple of the period of the signal. Okay, and that is what happened in general. What is the Fourier transform of this? What is the frequency domain representation of these two signals? We can see that by looking at the second picture. Here we go. Here, as you can see, we are not having any information that there is a frequency at 1 hertz in both the two pictures. As you can see, the lines, the vertical lines, the vertical segments are not telling me the same picture as the previous one. Just because we have an observation time that is not equal to a multiple of the period, okay, of your signal. And if you fictitiously increase your signal by adding lots of zero, what I call the zero public technique, we are having the other curve, bottom and upper, okay, that is the one that is considering all the previous information from the sinusoidal wave, but it is adding 5,000 samples, okay. The information is a lot more fine with respect to the previous one, but however, it is passing through the same points, of course. And as you can see, there is a very rough identification of the frequency of your sinusoidal wave, but also the amplitude. It should be 1. Instead, we are about 0.6, 0.7. We don't know where we are, actually, okay? And that is the aliasing problem in real life. Now, let's go down once again, okay, and then let us use, okay, the different sampling rates, okay, just to see what's happening if we are having the same signal, but this time with a higher, okay, sampling rate with a truncated data that is equal to 1.5 signal. Sampling rate is 20 times the TP, okay, so it's 20 samples per period. Let's build our signal. Let's have the frequency domain representation using the Fourier transform, and let's plot this once again. So, and here we are. Because we increase the number of samples in time domain, the identification is a little bit more accurate than before, but we are not able to fully solve the problem, the leakage problem, okay? Because as you can see, we are having, the case of 30 samples, we are having, let's say, additional frequency with respect to the other one that are popping up from the x-axis, okay? That is typical evidence that there is a leakage problem. Now, let me introduce the windowing function. We already discussed the windowing function, so the Bartlett, the Hanning, the Hamming, the Parseval, Kaiser-Bessel, flap-top window function, windowing function. All of these functions are being already discussed during our classes. Let me show them. Okay, and here is the representation of all these windowing functions. We are considering the blue one is the original sine wave with the frequency at 1 hertz. Okay, and the other one is observed is the same function but observed with a longer observation time, 1.5 the period this time. And the other curves, the other color curves are the ones that are, let's say, modified by introducing the windows that we consider, part the Hanning, Parser, Kaiser, and that we can see together. Okay. The uniform one is the one that is just the observation time from 0 to 1 or 0 to 1.5. Okay. It doesn't do anything about that on the signal. The frequency domain representation. There we go. And once again, the bandwidth is only 0.10 hertz because we have a sampling point of 20 hertz. Okay, and as you can see, there is a reduction of the detrimental effect of the leakage in your frequency domain representation. However, we also have a reduction in the amplitude of your signal. So, as we already discussed in our classes, in our courses, the leakage problem is not possible to fully remove, but we can reduce as much as possible according to the different window function that we are using. Okay, and finally, the last case, we are writing our own self-system transfer function. Okay, we consider the free response of a single degree of freedom system. The sampling frequency is 100 Hertz, the observation time is 5 Hertz, the natural frequency of the system is 2 Hertz, and then the damping, the theta, the damping coefficient is zero point 0.3. Okay, we, um, we write that, we plot this result, and also we use this result also with a noise. Okay, we corrupt this response process function using some Gaussian noise, and then we evaluate what is the effect of your frequency domain representation. Okay, using this this signal. Okay, we are almost ready. Yes. Okay, and that is your result. We have the effect of the time truncation, time the number of data with respect to noise, with respect to the whole of the zero padding. Okay, so we have some comparisons between what could be the actual frequency band representation of your system transfer function with respect to what we could have when considering a reduced number of points, noisy or noise-free. Okay, so I leave you the discussion of these. And that is, of course, the corresponding time domain. And as you can see, there is not that much to consider here in the time domain. The effects are more visible in the frequency domain. Okay, the last is the FRF estimate. Here, what we are doing is just defining a system that is a 2 degree of freedom system having two natural frequency, one are 5 and the other one are 15 hertz. Okay, we define your impulse as a function. We make the system frequency transformation of that, and we evaluate the output of the signal. We use some additional Matlab routines that I leave for your analysis. So please review that in the Matlab, but it's just making a convolution in time domain. And let's see what's happening with that by using different estimators. We know that H1, H2, and here I also brought the HV estimator. That is in a sort of in between the properties of H1 and H2. As the common window is telling us, we have to wait patiently. Yes, we are still waiting for you. Please do that fast if you can. Maybe, yes, time for a coffee, just a few seconds. Let me end the class. I'd be very happy to have a coffee. It is a pity that we are not here all together. I could offer you a coffee, but yes, an espresso also is okay. And then we are done, hopefully. Yes, here we are. So let me explain you what we got. So the first one is the case in which we are using the H1, H2, and HT estimator having output at the noise output at the the noise at the output stage only. The dot function is the ideal one, and we are reporting that in terms of amplitude and phase. There could be some optimal usage of this H1 or H2 according to the different stage in which the noise is affecting your analysis. So this is the case A, in which we are having output noise only. The second picture is referring to the input noise only. Okay, and that we still have a comparison between H1, 2, and HT. Then we are having option number 3. We are having both the noises, both the stages, input and output, and then once again the comparison between each one, okay. And finally, the last plot is an evaluation of the coherence function. As you can see, it is quite high, not that high, and that is the effect of noise that is reducing dramatically the coherence function, especially when you are in the case C and A. Okay, okay, that's it. I'll leave you the information of the HV straight on the Matlab file that I wrote for you. So that's it. What you still have to do is to make your own estimate of the system properties when I give you this beam experiment.mat. This beam experiment.mat is a file, Matlab file, that is having the input and the output, random input, random output, okay? And we are having the information that the sampling frequency is 256. So you have to use this data in order to estimate your system properties using your estimators, the best one that you prefer, using the time to frequency transformation as we use and as I show you in the aliasing and leakage Matlab file. Okay, so sort of put all the things together, all the things that we saw together in this laboratory activity in order to use those experimental data that are coming from a cantilever beam, I can tell you. Okay, so these Matlab subroutines, aliasing, leakage, and FRF will be available at the course website as well as the laboratory activity number 3 text so that you can have the idea of what you have to do and what you have to discuss. And once again, write your report so that you can put all your ideas, first all your results, and then all your ideas in why you have you achieve some result with respect to the other one. How can you solve the problems using in our laboratory number 3, let's say windowing function and other options. Okay, that's it for today. Thank you for your attention. Questions?
Professor, I have a question.
Yeah.
I don't understand why we have to do the zero padding and its effect on the frequency domain.
You don't have to do zero padding. Sometimes this is done in order to increase the frequency resolution, fictitiously increase the frequency resolution, because you are adding more data that are all zero. And sometimes this increase of frequency could help you in understanding the behavior of your system. Okay, and this example is written here. I'll try to, yes, okay. If you look to this result, for example, which we are having the leakage problem, and you stay on the original data, that could be either 15 samples or 35 samples, okay, you have a system representation that is the one that you have, okay. If you introduce additional samples via 5,000 samples, zeros, okay, you are not introducing any new information at all, but from the dotted line, you can easily understand where your frequency, okay, of interest is acting, okay? For example, 1 Hz in these two pictures, okay? It is just to maybe help the understanding of the system, help to reduce some noise effect, okay? Help to have a better use because you are increasing the frequency resolution. But however, you are not solving the leakage problem.
Okay, thank you.
Welcome. Any other questions? Okay, if not, thank you so much once again. I'm sharing all this data with you in the course website, and of course, feel free to contact me if you have any issues on the Matlab routines or some other issues during this laboratory number. Okay. Thank you and have a great weekend. See you on Monday. Bye-bye.